All right, so this presentation is on the geometry of a dynamic tetrahelix and field structures. I'll be using physical models, and a physics simulator will be used to explore the various properties and behavior of the tetrahelix structure in a potential relationship with field structures. So first I'll start with the basic element definition for a tetrahelix. Where we have a tetrahelix is defined as a sequence of face-connected tetrahedrons, or elements. And one face of the tetrahedron is defined as the input face, and the other face is defined as an output face. And an arc shape can also be used as an element of the tetrahelix, which more clearly reveals its internal structure and geometric properties. So let's go through some of the construction terminology. So the first element of the tetrahelix is considered the oldest element, and then subsequent elements are considered increasingly younger elements. And the output face of the older element connects to the input face of the next younger element. And the younger elements can only rotate around the axis centered on the output face of the older element. So this is just a simple example of building a tetrahelix constructed one element at a time, and each element is considered progressively younger and establishes the direction of the tetrahelix. Now we'll look at the rotation axes and angles of a tetrahelix. So I define a bend angle as the angle between the input and output face of the tetrahedron, or the dihedral angle. And a twist angle defines the amount of rotation used at the face-to-face connections, and it's perpendicular to the output face. And each element of the tetrahelix can be rotated with a step of the twist angle, and the default is 120 degrees for the classical tetrahelix. And a sequence of digits define the twist angles used at the elements for the tetrahelix, and where 0 indicates no step or no rotation, 1 indicates a clockwise step of 120, and 2 indicates a counterclockwise step of 120. So these are your three twist options for a left twist, no twist, or right twist, with the internal arc shown. And then this is a view of using an arc element for the tetrahelix. And this helps reveal the internal structure of the tetrahelix and how its elements interact with each other. So this is just the arc definition. So the arc is created from the intersection of a torus and a tetrahedron. And the torus is centered at the midpoint of an edge of a tetrahedron and passes through the center of its adjacent faces. And the arc shape still retains the essential geometric properties of the tetrahedron used in the classical tetrahelix. So here are some construction examples where a tetrahelix can be defined as a sequence of digits, 0, 1, or 2, and they represent the twist angles between the elements. And a unique subsequence can be used to describe a tetrahelix, where its total length is typically defined in multiples of the subsequence bit length. And here are just a few examples of a tetrahelix that uses a 3-bit subsequence and their resulting structures that could be built within a simulator. So now I'll just start this video that shows an example of building a tetrahelix. So the oldest element is fixed in world space, and I'll be using a subsequence of 0, 0, 2 to construct a tetrahelix from tetrahedrons. Then if I replace this element with a transparent version of it with an internal arc, it reveals internal structure a bit more clearly now that you can see the twists involved. Or you can just use a simple arc, and that can actually reduce some clutter to see a bit more of the architecture or the structure inside the tetrahelix. I'll be using these arcs to describe the different subsequences I'll be playing around with. Let's show that one. So this is the classifications of different types of tetrahelix. And generally, there's three main classes of a tetrahelix that fall into these categories. There's a linear tetrahelix that twists along a primarily straight path, or a spiral tetrahelix that twists along a spiraling path, and a loop tetrahelix that twists within a circular path. Now, these are just some examples of a linear tetrahelix and their associated subsequence listed below. I'll just show a couple examples of a spiral tetrahelix that can be built in a simulator. And then these are just some of the subsequences I use to create them. And these are examples of some loop tetrahelix and their associated subsequence. And for a loop tetrahelix, there's going to be a gap that will always exist. And in fact, that the primary focus for the rest of the presentation is going to be on loop tetrahelix. And they almost form a closed loop circuit. But the elements in a loop tetrahelix are not perfectly aligned. So it'll be this gap between the oldest and youngest element. But I found a simple way to close this gap, which can create a closed loop circuit. And this will be done with the introduction of a dynamic tetrahelix that introduces a twist motion into the structure. So now I'm going to start describing what the dynamic tetrahelix is. So up until now, the tetrahelix that we've explored have been static with no overlapping elements. In this section, I'll be using the simulator to introduce some dynamic behavior to the tetrahelix by modifying the twist angle between its elements. And I call this twist angle scaling. And this will cause the structure of the tetrahelix to expand or contract, and the elements of the tetrahelix will move along this ever-changing circular curvature. And to examine the inner structure of these dynamic tetrahelix, these elements will be replaced with a simple arc shape. So this is just a little bit on the simulator uses a physics simulator that uses a parent-child relationship or recursive parenting to define the connection and location of the elements in a tetrahelix. An example we have here is a tetrahelix with a length of 3, elements 1, 2, and 3. And then from a generational perspective, any element could be both a parent and a child. If you look at the first generation, element 1 is a parent of element 2, which makes element 2 the child of element 1. You move into the second generation, element 2 now becomes a parent of element 3, and element 3 now is a child of element 2. And that's recursively done to build out a tetrahelix. So now let's look a little closer at the relative positioning of the elements and the motion inside the tetrahelix. So the oldest element, again, is fixed in world space, and it's a parent of the next element or child added to the tetrahelix. And the child's position is not defined in world space, but in a local space relative to its parent's output phase. And then this child could become the parent of the next element added to the tetrahelix. And then this is repeated recursively until all the elements are added to the tetrahelix to form this chain of connections. Now, this video is just going to show how the younger elements accumulate motion. So when a child moves at the end here, you see it's going to have no effect on the position of its parents or its ancestors. But when a parent moves in space, its child and all its descendants move along with it because their local space reference has changed as a parent moves. So every child inherits the accumulation of motion from all of its ancestors. And as a result, the youngest elements move faster than the older elements because they've got more ancestors to accumulate motion from. So let me describe a little bit what twist angle scaling is doing. And now that we know how the elements of a tetrahelix are connected, let's introduce some twist motion to the structure. So the default twist angle step in a classical tetrahelix is 120 degrees, but a simulator allows this step to be dynamically modified. So for example, if the twist angle step is changed to 150 degrees, then the simulator will do the following based on the current subsequence for the tetrahelix. For digits 1 in the sequence, the twist angle would change from 120 to 150. For digits 2 in the sequence, the twist angle would change from minus 120 to minus 150. And for digit 0 in the sequence, the twist angle is unaffected and remains at 0 degrees. And again, with the oldest element fixed in world space, the twist angle scaling will cause the younger elements of the tetrahelix to extend or contract, which create this twisting motion. So this is just a diagram with two examples of twist angle scaling. And the blue arrows represent the default rotations of 0, 120, and minus 120. But when I change the twist angle to 150, the magnitude of the rotations both increase in different directions and sort of trending towards 180 degrees. But if I make the twist angle smaller, the absolute values now decrease in a different direction, but trend towards a 0 degree rotation, just to give a visual of what's going on. So again, this is just a dynamic twist angle example. Again, if the oldest element is fixed in world space, and it started with older elements first, the simulator makes incremental changes to the twist angle, and as the older elements rotate, all the younger elements connected to it have their frame of reference changed, and as a result, experience accumulation of motion from the older elements. And the simulator repeats this process, and the tetrahelix starts moving, with younger elements moving faster than the older elements. Now we'll look at a similar example with a loop tetrahelix with this subsequence here. And it starts with a gap at the default twist angle of 120, you'll see here in the top right corner, and just a slight change to the twist angle to 120.43 degrees causes the tetrahelix to extend until that gap is closed. I'll just show that again. And at this point, the output face of the youngest element aligns with the input face of the oldest element, and a closed loop circuit now can be created by making a connection between the oldest and youngest element to complete the circuit. All right, so now that we know what the dynamic tetrahelix is about, we're going to look at these harmonics that show up in these structures. So up until now, the tetrahelix that we've explored didn't have any overlapping elements. In this section, the simulator is going to allow the elements to overlap. And to examine the inner structure of these dynamic tetrahelix, its elements will be replaced with a simple arc shape. And as the twist angle is scaled, the tetrahelix will begin to smoothly twist around itself. And at certain twist angles, the arcs completely overlap and align to form these harmonic repeating patterns that also create closed loop circuits. So as a concept, could these closed loop circuits be used to model field structures of some sort? It's an open question. Now here's a little bit more detail on what we're looking at in the harmonics. So when the twist angle scaling is applied to a loop tetrahelix, it reveals these harmonic patterns as the elements align and overlap, and they move along this ever-changing circular curvature. And each unique tetrahelix subsequence represents a family of harmonics, and they can have a different magnitude. And the magnitude is equal to the total length of the tetrahelix divided by the bit length of its subsequence that was used to define it. Now the magnitude is similar to frequency, but there's also a frequency component to the subsequence itself of ones and zeros. So I wanted to keep that separate for now, and I'll just be using magnitude instead of frequency. So in the next video, I'll be using a subsequence here of 21, 12, 12, 12. Be used as an example to illustrate more detail some of the various harmonics with different magnitudes within this family. The total length of this tetrahelix will be set to 16. The subsequence has a bit length of 8. And this represents a harmonic with a magnitude of 2, or the second harmonic. Then the total length of the tetrahelix will be increased 8 elements at a time to illustrate some of the higher level harmonics that exist for the subsequence. So this is an example where this particular subsequence with a default twist angle of 120 degrees forms an open loop. Like these, that's sort of the gap that would exist. But now if I change the twist angle down to a particular angle, around 112 degrees, then the youngest and oldest element, here the red and blue arcs, now overlap to create this closed loop circuit with this second harmonic pattern. Now I'm going to rebuild the same tetrahelix with the same subsequence with 8 additional elements in it. And you'll see now here that that broke the closed loop. If I continue now to change the twist angle, I can extend the tetrahelix to a point where now the oldest and youngest overlap again, and they create this third harmonic. I do this a couple more times by adding in another 8 elements, for an example. And if I change the twist angle, I can get up to the 4th level harmonic, where you create the closed loop. I'll do this one more time to show the 5th harmonic for this subsequence. And it now, this particular twist angle, creates a closed loop. And this loop here is what I call the 5th harmonic magnitude for this subsequence. But I want to point out also that these higher level harmonics inherit the low level harmonics that I just showed you for the 4th, 3rd, and 2nd harmonic. However, they don't create a closed loop because the length is not the same as the 5th harmonic, but they still overlap in the same pattern. So when I restart the video, I'm going to now decrease the twist angle, and the tetrahelix is going to sort of contract and goes back to form the 4th level harmonic here. Keep on decreasing it. It gets to a 3rd level harmonic. There's an interesting right one here where this creates a 5th level harmonic. It's a fractional harmonic that is I'll be referring to later on in the discussion. It just shows up in the subsequence. And I can continue to reduce twist angle. I'll freeze it here. So now this 5th level harmonic is converging on the 2nd harmonic pattern, and it does such in a way that these loops overlap itself, and when they get down to that twist angle, it appears like one loop, but there's actually multiple loops around this structure where the 5th harmonic has inherited this 2nd level harmonic pattern from the lower level harmonics. Now this is just a video clip that's going to show a number of other examples. You can see up in the status bar different subsequences of using different subsequence lengths. Total length are different. And then this represents the twist angle, where these subsequences make closed loop structures where the oldest and youngest overlap to create that closed loop circuit. So this, again, several different examples of different subsequences with these unique patterns. As we get to the last one here, I'm also going to now start changing the twist angle for this subsequence, and I'm just going to expose the other harmonics that are embedded in this subsequence. When you change the twist angle, it'll basically change along this curvature and create various different harmonics as well if you dynamically change the twist angle. This is a slide I just wanted to show that I found 2 different types of loop tetrahelix that have different behavior when the twist angle is set to 180. And in one case, at 180, the tetrahelix forms a linear wave structure. And when it decreases to 0, it forms a ring. And in the other case, at 180, the tetrahelix is constrained to a circular disk, and then when it decreases to 0, it also forms a ring. So the next two videos are just going to illustrate these two different behaviors. So in this case, we're starting with this linear wave structure. As the twist angle is changed, it starts exposing this ever-changing curvature, along with creating all these harmonic patterns that it races through. And the diameter of these loops decrease, and it wraps around itself several times. There's only one axis of symmetry that I'll point out later on. And at 0 degrees, it collapses into a ring. Now, this next example, the different subsequence that has a different behavior at 180 is contained to this circular plane. And as it decreases the twist angle, like the other one, it reveals all these various subharmonics. You know, that diameter changes, it wraps around itself numerous times. Again, just one axis of symmetry, and it collapses down to a ring at 0 degrees. So I just came across these two different types of loops, or tetrahelics, that have this behavior. This next section, I referred to a fractional harmonic earlier. I'm just going to explain the details of what a fractional harmonic is. So the main harmonic of a tetrahelix occurs when that first loop is created and forms a closed loop circuit. But when the twist angle is decreased further, a second overlapping loop forms, and this reveals a fractional harmonic. And as the twist angle continues to decrease, additional fractional harmonics are revealed for each new loop or each new lap, and this defines the depth of the fractional harmonic. And each additional lap around itself, the depth of the fractional harmonic increases by 1. Now I'll be using M to represent the magnitude of the harmonic, and D represents the depth of the harmonic, or the number of laps it goes around itself. And I'll be using this M dot D as a generic description for these harmonics. So for example, a 7.2 harmonic would be a harmonic of a magnitude of 7 and has a depth of 2, or it takes two laps to get around itself. And then a 7.1 harmonic would just be the main harmonic that could also be referred to as just a 7th harmonic, because it's closer than one lap around itself. So now we're going to look at one example of the 7th harmonic for this particular subsequence. And in the next video, the simulator is going to apply a continuous twist angle scaling to this loop tetrahelix. Now we know the subsequence has a bit length of 8. I'll be setting the tetrahelix length to 56 elements. And this is going to reveal the 7th harmonic, which I got from 56 divided by 8. And in the video, the twist angle is going to be continuously scaled from 180 to 40 degrees. And the tetrahelix is going to transform from a linear wave into progressively smaller loops. And as the arcs overlap, they form various harmonic patterns. And eventually, as the loops get smaller, they wrap around itself, creating multiple overlapping loops. And each lap around a loop reveals a different depth for a fractional harmonic for this subsequence. And this table just highlights the 5 different fractional harmonics, 7.1 through 7.5. And this first column, this represents the twist angles where the closed loop gets created. So now I'm going to start this video, and it's going to start decreasing from 180 degrees. And at about 158 degrees, it creates the 7.1 harmonic. I continue to decrease the twist angle, and now it's made a second loop around itself at a particular twist angle, and this creates a 7.2 harmonic. Now I can continue to decrease the twist angle. This is the third time it's wrapped around itself. That creates a 7.3 harmonic. continue doing this, it creates a 7.4 harmonic on a fourth lap around itself, and then the final harmonic shows up to create the 7.5 harmonic. So these are the only 5 twist angles that create an exact closed loop circuit for this particular subsequence. So we can see that the same harmonic number occurs multiple times at different twist angles, but they form different patterns that are called fractional harmonics. And each lap around the loop represents a fractional harmonic where the number of laps indicate its depth. So an analogy for this fractional harmonic can be shown in a heptagon/heptagram system where it requires one or more laps around itself to connect its vertices as its interior angle decreases. So if you look at the heptagon, which is also referred to as the 7/1, you can connect its adjacent vertices in one lap around its perimeter. Now with the interior angle decreasing, we get to the heptagram, referred to with a 7/2 version, where every second vertices be connected, but it takes 2 laps around its perimeter to make the connection. The interior angle gets decreased further to create the 7/3 version of the heptagram. And this is where it takes every third vertices connected, and it takes 3 laps around the perimeter to make those connections. So we see analogies to this in other geometric shapes. So this slide, I referred to it earlier. Each unique subsequence of a loop tetrahelix represents a family of harmonics. And the total length of the tetrahelix determines the actual magnitude of the harmonic. And the higher level harmonics inherit the patterns from the lower level harmonics. And this table just shows the family of 7th harmonics for this particular subsequence. And you'll notice in the white rows, that harmonics for the 2nd through 6th harmonic show up in this table, sort of interspersed between the green rows. So the green rows show what I shown earlier are the 7.1 through the 7.5 harmonic, where they create the closed loop. And interspersed among that are these white rows that represent the lower level harmonics, where the length would be a shorter length. But at these particular twist angles, they come up with a low level harmonic pattern. Now let me just go to the next slide that shows the video. So now I'll be showing the harmonics represented in this table here. And I'll just be looking at the harmonics between 7.1 and 7.2. I'll stop at this point as we've created the 7.1 harmonic, the first time we've closed the loop. I'll decrease the twist angle slightly, and it'll get to a point where it overlaps the same pattern. And this is actually the 6.1 harmonic. It's no longer a closed loop circuit because of the overshoot here, but it shares the same pattern as the 7th harmonic. And I'll do this a couple more times to show the 5.1 harmonic that it inherited. At this point here, it's going to show the 4.1 harmonic. It still shows up in the 7th harmonic. And then as I continue to decrease it, I'll stop it at the 7.2 harmonic, where it creates that closed loop for the 2nd time. Now, if I go in the opposite direction, I can introduce higher level harmonics by increasing the total length of the tetrahelix, again, for a given subsequence. And this table just shows a portion of the harmonics that occur when the total length is increased from 56 to 160 elements. And this reveals the 20th harmonic, which is 160 divided by 8. And the next video is going to illustrate this table and show some of the 20th harmonics and their patterns. And the other things this video is going to show is how the accumulation of motion has increased since we have now a longer tetrahelix, the younger elements have more motion to inherit from more elements. So you'll notice that the elements now are moving quite a bit faster than they were for the 7th harmonic that I showed. And I guess an analogy to this is motion in a bullwhip, where the sections furthest away from the handle move faster than those closer to the handle. And I'll just restart up the video and point out a couple of the high-level harmonics that we hit at certain points. That would have been a 19th harmonic. That's a 14. That's a 9-level harmonic. There's a 13th, a 17th. And now it's going to wrap around itself, and at this point it looks like a 4th level harmonic because there's only the patterns visible, but in fact this is wrapped around itself 5 times to show the 4th level harmonic that's visible within a 20th harmonic structure. Now both the 7th harmonic that I showed earlier and this 20th harmonic, they all reside on the same curvature, which is determined by the subsequence itself. Now this is just showing some of the raw data that I can extract from the simulator. So these tables just contain, in the first column, it reveals the twist angle and the associated harmonic value in the second column. So 53.050 is the 53rd harmonic with a depth of 50, meaning it took 50 laps around itself to create the closed loop. And with the 2 different tables, table 1 has been sorted by increasing twist angle, and the second table is sorted by increasing harmonic value. Now at first glance, you can't make much of the data as far as any patterns or predictions. So in the next slide, I plotted this on an XY scatter plot, and it does reveal some interesting groupings and trend lines that stood out right away. So this is a plot of the twist angle on the x-axis versus the harmonic number on the y-axis. And this is a plot for the 67th harmonic for this subsequence. So it's a very long chain of elements. And this plot actually contains about 2,400 data points. And now you can start seeing some interesting groupings and trend lines here that have a unique fingerprint for this particular subsequence. In the next slide, I found some interesting groupings that I'll explain. So if you look at this red horizontal line at the bottom, this actually represents the 7th harmonic I showed earlier. Now this is in the form of 7.d. So this is the 7.5, 7.4, those 5 harmonics that you saw in an earlier video. These horizontal line, or the vertical line here, just indicates a particular pattern that shows up at this particular twist angle. And each data point, as you get higher along this axis, is the same pattern that shows up, but it's got more loops that overlap to create the same pattern. Over on the right here, this yellow highlighted line here, this indicates all of the harmonics with a depth of 1. So this is where the first closed loop circuit is created, and they all group into this sort of trend line. In fact, all of these different trend lines here show an increasing depth. So the next one over is an M.2 that show all the harmonics which have a depth of exactly 2. The next one over shows all the harmonics that have a depth of 3. And they're just grouped nicely in this plot, which I found interesting. Another little trend line here, if you actually look at the data, there's always going to be a 20 difference. If you look at the magnitude and the difference between its depth, it's always going to be 20 for every data point along this curve. You know, one curve up here would just show a difference of 21. There's some interesting groupings like that. This highlighted line here, the magnitude jumps up by 3 for each time the depth increases by 2. So just a number of interesting groupings that are visible in this plot that I found interesting. And the other thing that was useful, so this would be the raw data that I would import into Excel. And at first I noticed there's some gaps in the data that I thought might have been an anomaly for a particular harmonic. But when I went back into the simulator and extracted the data manually, there was indeed a data point here that I had missed because I hadn't set the sensitivity in my simulator fine enough to capture every data point. Because you notice that with these longer tetrahelix, the elements move quite fast. And if I didn't have the step of the twist angle small enough, it just skipped right over this harmonic and I missed the point where they overlapped. So these plots helped me find all the data I needed. This is just a completely different subsequence, and it has like a unique fingerprint. So each subsequence, if you plotted their data, would just have some unique profile that could uniquely identify these subsequences. So now we're going to move on to a structure that I call a core field structure, and I'll also be describing a modified tetrahelix system. So the tetrahelix with this subsequence that I've been using of 21, 12, 12, 12 has some unique transformational properties not seen in other tetrahelix. So at a twist angle of exactly 60 degrees, this tetrahelix forms into a structure that has 4 axes of symmetry, like that of a tetrahedron. And all the other tetrahelix that I've examined so far only had 1 axis of symmetry. And I'll be referring to this tetrahelix as a core field structure, or a CFS. And this may be useful in modeling field structures. And I'll also introduce a new tetrahelix construction method for exploring the CFS called a modified Tetrahelix system. So the CFS has similar geometric properties like that of the Clinton field structure, referred to in field structure theory by Don Bradell, except that the CFS allows for overlap in its structure. Could these closed-loop circuits be used to represent or model the behavior of field structures? So to address these questions, I'll just take a deeper dive into exploring the properties of the CFS structure. So the next video is just going to illustrate the transformation of the subsequence from a twist angle of 180 to 60 degrees. You'll see that at 180, it forms a linear wave structure we saw. And as the twist angle decreases, it forms a number of fractional harmonics. They all have one single axis of symmetry. But at a twist angle of exactly 60 degrees, the Tetrahelics transforms into a CFS with 4 axes of symmetry. So we start at 180, and as the twist angle decreases, you see the loops get smaller. These various harmonics show up along the way. There's only 1 axis of symmetry for each of these harmonics. And as we converge onto 60 degrees, it transforms into that CFS structure that now has 4 separate axes of symmetry that hadn't showed up in any other of the tetrahelix I've explored. So now I'll explain what this modified tetrahelix system is. And after full examination, I realized that the twist angle of 60 degrees has some very interesting properties that transform the behavior of a classical tetrahelix. And I developed this new tetrahelix construction method for exploring the CFS called a modified tetrahelix system. And this tetrahelix uses a different set of twist angles that have been phase shift inverted by 180 degrees. And as a result, the model uses 3 different twist angles of 60, 180, and minus 60. And these new twist angles are represented in the subsequence with the following digits, where 1 equals 60 degrees, 3 will represent 180, and 5 represents minus 60. And as a result, the subsequence now will have a sequence of 15, 15, 15, 51 when you construct it as a modified tetrahelix. And the remainder of the presentation is going to focus on these unique properties for a modified tetrahelix. And I won't use any twist angle scaling for the next few slides. So this is just a diagram that illustrates this phase shift inversion I'm talking about. So in blue here is a classical tetrahelix with the 3 rotations of 0, 120, and minus 120. If you rotate these axes by 180, you get the result in this red diagram, which shows the 3 new twist angles of 60, 180, and minus 60. So all the modified tetrahelix we'll be looking at will be based on these different rotation values. So from a classical tetrahelix perspective, the phase connections now in a modified tetrahelix aren't flush. They're phase shifted by 180 degrees, but the phase centers are still aligned with each other. Now this is just a view of using arc elements to construct a modified tetrahelix. And this allows us to look more closely at the internal structure of the CFS, and also reveals the interaction and overlap of the elements within this modified tetrahelix more clearly. So if we take a closer look at the internal structure of the CFS, referring to the vertex here and the edges, at first glance, the CFS only appears to have 18 arcs. If you count up 3 for each of the 4 vertices for 12, 1 at each of the 6 edges for 6, when in fact the CFS is constructed from 24 arcs. So there's some overlapping arcs in the structure, and this is actually an integral property of the CFS. In the next video, I'm going to change the twist angle slowly to reveal these overlapping arcs. So you see now, as I change the twist angle, the edges separate and now expose the 24 arcs that are inside the CFS. Let me introduce this model here on the left that's going to be used in the next video. So this is a truncated octahedron. It's got the same arc that I've been using inside to show the connections. And it's a geometrically equivalent element that I'll be using in the next video to help visualize the structure of the CFS. So we'll be starting with the CFS structure. And then I'm going to be replacing its elements with the truncated octahedron I showed you earlier. And this truncated octahedron is a space-filling structure. But if you look closely, this now reveals that there's only 10 unique element locations that the 24 arcs of the CFS reside on. And the gaps between these truncated octahedrons are yet another truncated octahedron. So it's sort of a 3D checkerboard of a half-populated space-filling matrix of truncated octahedrons. Now I'll be replacing these with transparent versions so you can get an idea where the CFS is located inside. So now I'm rebuilding with these transparent versions with the arcs visible. And now you can see the vertex of the CFS showing up here, which is actually just one location. It looked at first like 3 unique arcs, but it's really just one location with 3 different orientations. And the edges we've already seen are actually overlapping with 2, and it really just corresponds to one unique location. So this sort of matrix of arc locations will be explored in more detail in a few more slides, but I just want to give you an idea what the internal structure of the CFS looks like. First, I wanted to go through some of these multi-loop Cfs configurations. So the CFS was discovered in the simulator constructed as a single loop modified tetrahelix. But after closer inspection, I found that the CFS can be created by bonding smaller modified tetrahelix together. So in addition to the single loop CFS, there's 3 multi-loop configurations for the CFS as well. There's a 2-loop solution, where each loop has a 12-arc loop. There's a 3-loop solution and a 4-loop solution. And I'm using physical models to construct these multi-loop CFS from smaller subcomponents. First, this is just a view of the single loop CFS, what it looks like in the simulator. It consists of 24 arcs. Each of the edges are actually a pair of arcs. And this is the full subsequence, repeated 3 times. If you follow those 24 rotations that these digits describe, it creates a closed loop that comes back on itself. Now, this is just an illustration of a physical model from a single loop CFS. And when it's constructed, the overlaps have to be resolved because it's a physical entity. And so the arcs can either be weaved together or they can be just set adjacent. And the flow, where these 2 arcs occur at the edges, could be in the same direction or in different directions. Now, weaving is not a requirement to hold the structure together because the arcs are bent and twisted into this form, and its own torsion will hold the structure together. So now this is the 2-loop solution. This is the actual subcomponent that I'll be using. It consists of 12 arcs. This is the full subsequence here. And if you follow that 12-bit subsequence, it creates this closed loop circuit that you see here. Now, this next video is going to use a physical model to show that CFS can be created from these 2 subcomponents. And when subcomponents are brought together, their arcs have a natural alignment with each other, and they form the same CFS pattern. I'm using magnets to hold them together with an adjacent bond. Now, there could have been weaving, but that would require an extra cut and rejoin step and an explanation to go along with it. Now, this is just the 3-loop solution for the CFS. This is the 8-arc subcomponent that we used, this sort of saddle shape. And this is the subsequence repeated twice that defines this closed loop structure. And in this video, I'm just going to basically demonstrate how the CFS is created from 3 of these subcomponents. And when they're brought together, they have a natural alignment, and they just kind of connect by adjacency to create the identical structure. But again, there is no cutting or weaving required. It can all be done by adjacent bonding. And next we have this 4-loop solution using this subcomponent, using this 6-bit subsequence of 1-5 repeated 3 times. And this next video is just going to illustrate the construction using these 4 separate hoops that create the CFS with these 4 subcomponents. And much like in the other videos, the arcs have a natural alignment, all within this matrix I'll be describing shortly. And again, they can be connected without any weaving or cutting because they just have a natural alignment with each other. So now I'll talk a bit more about this matrix that's found within this modified tetrahelic system. And the elements in this modified tetrahelix of any subsequence are constrained to a predictable matrix of possible locations. So this is different from the classical tetrahelix, where the elements exist on non-repeating locations. So this is just a subset of the matrix I'm referring to. And any structure created using a modified tetrahelix will have its arcs constrained to a predetermined array or matrix of possible locations you see in this diagram. And this matrix can also be represented as an array of CFS that will be seen in the next video. And the void between these CFS creates these tetrahedral shapes created by their merging elements you can see here in this diagram. So this video is just going to illustrate how the arrangement of 4 CFS can be bonded together, and they create a void this tetrahedral shape at the center. So a combination of this void and the CFS creates sort of a space-filling matrix. And these arcs in this matrix represent the only locations that could be used in a modified tetrahelix. And the next video is going to illustrate a larger version of this matrix. And another way of looking at it, you'll see in the next video, in addition to looking at it as an arrangement of CFS, it also will be an array of vertex-connected tetrahedrons, which I'll show in this video. So it's just a larger subset of this matrix. You can see that these tetrahedrons are connected by their vertices that can also describe this matrix. And any subsequence I use and build a tetrahelix will be constrained to the arcs on this matrix, assuming if it's extended out in infinite directions. The elements cannot exist inside these voids. They are constrained to these particular arc locations, which is interesting. Now, this is just another way to visualize this matrix. And before I start, just imagine there's a virtual matrix in space, like we saw in the previous video, that extends infinitely in all directions. And this video just takes 9 random modified tetrahelix, different subsequences, builds them on top of each other, and no matter what subsequence I used, all the elements are constrained to this virtual matrix somewhere. And any intersection between the modified tetrahelix occur as perfectly aligned arcs within this matrix. So here are a couple of features that I thought would be interesting to apply to field structures, is that the overlapping arcs in this matrix could represent different intensities, different field intensities in a field structure. These converging diverging junctions at the vertex could support loop transformations within a field structure without disrupting the loop structure itself. I've got another slide that tries to explain this a little better. And then the overlap at the edges of the CFS also support sort of a bidirectional flow within a field structure that may be useful. So in this video, I'm just going to show how by adding additional arcs to the structure, they get absorbed and they introduce additional dimensions to the structure. Now in the simulator, additional arcs occupy the same space and they just appear as a single arc. But when I use a physical model in this example, the overlaps get resolved, and the overlapping arcs in the structure could model field intensity differences by adding more arcs. Now this is a continuation of the previous video. It just shows now after a number of arcs are added and get resolved, they create these membranes and tube-like structures, and they add an additional dimension to the structure that could also be useful in modeling field structures. This is the converging diverging junction points I referred to within the matrix, and this shows where 2 tetrahedral vertices are joined together. And these junction points could allow for a redirection of flow in a field structure without changing the location of the elements. So if you look at the green arcs in these 3 examples, you can come into this junction and come out in 3 different directions at the bottom without actually changing the actual structure. So there would be some switching function going on at these converging points, which I can't explain the mechanism to do that, but it's just some food for thought now of what this structure could support. Another idea that came to mind is there might be some natural attraction at these junction points that would increase the stability of the structure within a field structure. And this is sort of analogous to the attractive force between the flow of electrons in parallel wires or circuits, where the intensity of the force between these circuits are proportional to the intensity of the flow of electrons that would allow and create these magnetic field lines around the circuit. And these red field lines are somewhat similar to the structure of these tube-like structures that form with the overlapping arcs in the physical model we saw. And the overlapping arcs could increase the bonding force within the field structure or a bonding force with other field structures. Again, this is just more food for thought. Now, this is just an example of the interleaving two of these systems together. And up at this point, we just looked at one instance of a modified tetrahelix. But in fact, two of them could coexist in space at the same time, which I'll show in the next video. So now I'm going to build a first tetrahelix in yellow in one subsystem. And then I'm going to add in a second one offset in space and rebuild it. This shows up in blue. And now these two different tetrahelix built in two different systems are perfectly interleaved with each other and would never overlap or interact with each other, which may be an interesting property that could be used. And in this final section, getting towards the end, there's another interesting structure with similar properties that have the destructor defined in field structure theory. And this was found within the matrix of the modified tetrahelix system. And this structure is referred to as the tetrahedral field structure, or TFS, and can be constructed as a modified tetrahelix. So you got the structure on the left here and two different perspective views of the TFS. This is just a physical model of the CFS that's created with this 36-bit subsequence that describes a closed loop circuit. This top vertex is unique compared to the other ones, which I'll refer to in a minute. Now, let me just show you the single loop TFS that we saw I just described with this 36-bit subsequence. Again, this defines a closed loop circuit within the modified Tetrahelics system. Now, you can also build a TFS from 6 subcomponents that are a 6-arc loop that you here see on the left. This is a very stable subcomponent and also shows up in the 4-loop CFS we saw in the earlier video. This is an example of a TFS that we constructed from 3 subcomponents. Now, this is the subcomponent, the 12-arc subcomponent that I'll be using in the next video. It uses this subsequence that defines a closed loop structure. But this next video is going to illustrate, starting with 3 of these loop structures. They're just connected in parallel. So these can be separated and then rearranged without any cutting or weaving. And when they're aligned properly, they form the TFS within this matrix that I've been describing. These are just 2 illustrations of how the field intensity of a TFS can be increased by adding additional parallel arcs. And now I'm just going to show some of the bonding between TFS. So the top vertex of a TFS can be arranged in either a clockwise or counterclockwise manner. And as a result, there's 2 different types of TFS. There's a right-handed version and a left-handed version. And these TFS can be easily bonded together by interleaving their top vertices without breaking or weaving the loops together. Now, when the top vertices are interleaved, their arcs have a natural alignment with each other to form this bond within the matrix. But since there are 2 different types of TFS, there's 2 different ways that these could be bonded together. There's bonding between 2 similar handed TFS and a bonding between 2 opposite handed TFS. We'll see this in the next video. The resulting superstructure, or double TFS, creates 2 enclosed tetrahedral structures, which will be shown in the next few videos. So here we have 2 opposite-handed TFS. They're going to be, the top vertices are going to be merged together. And when they're merged, the arcs align perfectly within this matrix to form this new structure. You can see the 2 tetrahedrons now created inside. This next video illustrates the bonding between 2 similar-handed TFS. We're going to be bonding it in a similar fashion by merging the top vertices together. It's going to form a similar structure with the two tetrahedrons inside of it, but the loop arrangements around the outside are slightly different, which I can show a side-by-side comparison in the next video. So on the left here, this is just the resulting structure when two similar-handed TFSs are merged together. And it's got these three lobes around the center of it with two arcs wide. And it shows up a little bit different with the bonding two opposite-handed TFSs. And the loop structure around the center of it just shows 6 single loop structures. And now this is just the final slide that's going to show a couple examples of other modified tetrahelix with different subsequences. You can see up here in the status bar. These all form closed loop structures somewhere on this matrix I've been referring to. And these structures could also be used as subcomponents and bonded in various ways to create more complex structures within the matrix. And this wraps it up and concludes the presentation. And the main intent of the presentation was to share my observations of these loop tetrahelix structures when motion is introduced. I've speculated on some ideas on how these structures could be used to model field structures. I'm looking forward to addressing any questions or suggestions you may have. Now let me stop sharing. Oh. All right, that wraps up today's presentation. Sorry I went a little bit long. Oh, I think you're on mute. All right, I guess we can end the presentation and we can follow up. Or actually, unless you have any questions right now, we could, I know I went past the 12 o'clock.
Thank you very much, Gary. It's very informative, and going to take me quite a while to digest all of it.
Yeah, it's packed a lot of stuff in there.
Oh, but it's your presentation is a wonderful presentation. Thank
Yeah,
you.
you may actually be demonstrating the actual nature of the electron cloud.
Yeah.
Yeah, I'm not sure what it implies, but there's something interesting hidden there that I can't really figure it out. But by sharing it, I'm hoping it might trigger some thoughts with other people to take it next step further. A little bit of thinking out loud.
Yeah.
Just brilliant, Gary.
Oh, thank you.
Because next week will be the follow-up roundtable where you all have had a week to chew on what you heard and seen demonstrated today, and come next week prepared with your long list of questions, and we'll work Gary over.
All right, sounds like a plan. All right, thanks, guys.
Thanks,
See ya.
Gary.
All right.
Thank
Wow.
you. Wow.
Wait, Kirby, you have something?
All right, bye now.
I hope to see you next week and have something then. I notice you avoid any use of plural for tetrahelix.
Yeah, I guess it's easier to say.
It is easier. Your only choice is probably tetrahelices.
Yeah, get a little tongue-tied sometimes. Well, I'm glad you sat through it. I know it was a long one. It was longer before. It took some effort to carve it down to an hour. I was going to break it up into multiple sections, but I didn't want to drag people in for too many meetings.
I better mention that I may have to miss a few meetings because of a coming conflict of interest. I don't mean to forget about it. I'll be back on, I hope. And I will say this, when we look at atoms and find out that the an atom like uranium, that begins to get radioactive after you pile on so many neutrons and protons, one can't help feeling that there are flows of currents going around the various protons and electrons in some patterns, and the patterns, as the complexity increases, finally the flows begin to interfere with each other in such a way that stability is eventually lost. And it reminded me a little bit about certain things that happen in your demonstrations as as those tubes get fancier and fancier, more complex and more complex, and intersections begin to get nearer and nearer. Just possibly an analogy developing.
Yeah, I see a lot of analogies that could be compared. It's just, the patterns just sort of have some underlying relationship to physics, I'm guessing. It's just sort of too beautiful not to mean something, unless it's purely an art expression. Yeah, Carl, just let us know. We'll be meeting on a weekly basis, so please join us when you can.
All right, great. Of course, congratulations. Amazing taking simplicity and showing how it advances, almost like evolution of creatures on the earth.
Yeah, it's a very simple concept, and even the underlying technology of the simulator is actually quite simple. It's just connected tetrahedrons, but it's just a simple twist the control, and all those patterns just kind of emerge without doing any animations or rendering. Just a simple twist, and so that's twist and a subsequence and a length, and this patterns just naturally fall out of it by making subtle changes to it, which I found interesting. Well,
Okay,
looking forward to next week.
There you go.